A very good afternoon to all of you. I will start the session by I hope the slides are visible and the audio is also clear to you, right? I will be starting the session by 2:10, okay? So let's other join the class, then we will be starting by 2:10. Just wait for 2-3 minutes. Okay, another thing is that I'm just keeping the assignment posted in the Google Classroom. So you need to submit the assignment by end of the day, okay? No need to rush. So you can just assigning this. I will be telling once again while all of other students are joining the session. I will be telling once again. So I'm just assigning the assignments. So after the theory session, you can. Yeah, okay. Thank you. Thank you, Debayan. Okay. So one experiment was pending, actually experiment number 10. So I will be covering experiment number 10 first, then I will be starting with the 15, 16 and rest part, okay? Actually we will be hardly getting maybe 7-8 weeks excluding all the internals and all these things. So you may think that ma'am is doing everything in hurry. So if you have any doubt, you can definitely ask me. So I will be dealing with your queries. Just wait 1 minute. It's already 12:09. So okay. So it's already 2:10. So we can start the session. So a very good afternoon to all the students present here. I hope that others will be joining the session. The thing is that every day I used to tell the thing that you people have to do this, that, all these things, because there is a huge gap that we are observing, okay? So let tell your friends also to do the classes, otherwise it is very difficult for others to uh, understand also, okay? Now let's start with the experiment. The theory portion has been covered by Nilanjan sir. So I am not taking too much of time to tell the theory. Rather than I will be going to the practical part. The nominal part of theory that is required, that I will be telling you, okay? Now, so let's see this one, what is happening here. This is the experiment where we are going to understand about the uh, XS3 to BCD conversion using basic gates, okay? So in this lecture we are going to implement this circuit diagram. If you want to implement this one, so many of you are not doing the circuits, and you are also, I have observed the thing, you are just sending some dummy files which is not required at all. If you do not want to do it, please do not do it, but if you want to do it, please do it perfectly, okay? right? So these are the ICs which are actually useful to implement the circuit diagram. Okay, so this is the AND, NOT, and this OR gate. Okay, now let's come to the truth table part. This part I am telling you that which BCD part is this right hand side part and the XS3 is the left hand side part. So I will be telling this example, like this part is basically the XS3, right? So this is the XS3 I can write, and this part is basically the 4-bit BCD number. Okay, now the shortcut method is that when you know what is the BCD, it is the 4-bit conversion of this all the decimal number. How many decimal numbers are there? There are basically 0 to 9, all these things. So it is the 4-bit representation of 0, 4-bit representation of 1 up to 4-bit representation of 1001 is the 9. Okay, so these are all the BCD right hand side part, this whole thing right hand side part. Now definitely when you are doing we have done the BCD to XS3, what you have done, whatever was the BCD you have added plus 3, right? So you can do it in a different way. The approach will be you write down the right hand side first, that will be easier for you to understand, right? So when you are doing that XS3 to BCD, I will be, for my case I will write all the BCD, valid BCD, those are 0 to 9. 0 to 9 are basically the valid BCD numbers. I will be writing it first. Okay, now what is this value? If you add plus 3 with the 0 0 0 0, you will be getting 3, right? So 0 0 1 1 is basically the XS3 of what? 0 0 0 0, that we know, right? Now can you tell me what are the values which are not present here? So because we need to actually calculate the K map of this A, B, C and D. Okay, so actually we are doing the K map for the column A, because we will be taking the left hand side as this WX, YZ as the input. Okay, and this are going to be the output, but for sake of my simplicity, because I will be the person who is going to write in the exam, right? So I am just talking in your perspective. So if I need a method that is easier for me to understand and implement in the exam hall, that I will prefer, right? So if I would have been a student, I should have remembered this approach, right? So 0 to 9 4-bit representation will be the output. Definitely plus 3 we will be adding, so 0 0 1 1 0 1 0 0, so that is the up to 9 plus 3 will be the 1 1 1 1, that should be the input. Now can you tell me which, so when you are plotting the K map, you have to take from 0 0 0 0 to 1 1 1 1. So which of the input for which you are not getting the valid BCD, can you tell me? The midterm, this is within your test, that is in the Google form I have created. So I have given this question. So for 0 0 0 0, are you getting any BCD? No. For 0 0 0 1, are you getting any BCD? No. For 0 0 1 0, are you getting any BCD? No. Right? So we are getting the BCD from which section? From 0 0 1 1, that is from 3, that is a 1 0 1 2, we are not getting the BCD. We are getting the BCD from 3 to 12. From here also if you see that up to 12 we are getting the BCD, but if you think about 13, that is 1 1 0 1, are you getting any BCD? No. For 1 1 1 0 14, are you getting any BCD? No. For 1 1 1 1, are you getting any BCD? No. So can you tell me what are the terms where you are going to put crosses? Because you have to draw the K map for A, for B, for C, for D, right? So for the 0 1 2, that is for midterm 0, midterm 1, midterm 2, you will be putting the which condition? Don't care condition, because you are having 3 to 12, you are getting this valid BCD. Similarly, if you think of this is 1101 is 13, right? For mean term 13, mean term 14 and mean term 15. For those cases also you will be getting don't care conditions. Okay, is it clear to you? So if I just go, I think it is understandable and you have understood this one previously. If I tell you multiple times, you will be annoyed. Okay, so still if you have any doubt, you can just ping me in the WhatsApp. I am going to the K-map. So if you see the K-map, which are the values I have told you in the don't care? I told you 0, 1, 2, and in this side it will be 13, 14 and 15. All those things will be in the don't care part, right? Because in the last slide itself we have found out was 0, 1, 2 and 13, 14, 15 will be don't care part. Apart from that, where we are getting 1 for A, we are getting 1 for A. For 1011 is what? This is 11. You are getting 1. For 1100 is what? This is 12. You are getting 1 here. Okay. Now if you just come to the next slide, you can see whether I have done this one or not. For this one, what is 0? This is 0, 1, 2. So definitely I have put crosses here. For this is 4, 5, 6, 7, 8, 9, 10, 11. 11 and 12 I have put 1. Fine. And this is 13 I have put cross, 14 I have put cross and 15 I have put cross. So it's correct. So for this case, if you want to solve it, it is going to be this. For this quad you will be getting Wx, this one, and for this part you will be getting this part common is Yz, and this what is the horizontal common part? 1 1 means W, right? So Wyz. Okay, this part one wrong thing is there. I should correct it. It should be x bar also. Okay. Now, similarly, if you just, this is the K map for A. Similarly, if you go for the K map of B. Okay, কেন হলো আমি বলছি. See, when you are doing the truth table, it should be starting from 0 0 0 0 to 1 1 1 1, right? But are we getting the don't care? Are we getting any valid BCD output of input 0 0 0 0? Can 0 0 0 0 be a XS3? No. Can 0 0 0 1 be the XS3? No. Can 0 0 1 0 will be the XS3? No. So for those, as these three values, where you are getting the 3? I am not understanding. So if you are thinking like this, where this is 3 is valid, that's why you are getting the BCD, right? So that's why I am not putting the cross here. Anyways, for B actually, if you think about the B, where you are getting the values? Can BCD be, yes, XS3 is 0 0 1 1, the corresponding BCD is 0 0, because from XS3 is whatever is this value, just see once, whatever is this BCD value, if you just do it reverse way, you just add 3 to get this one, right? If you just add this to get this one, you will be getting 0 0 1 1. So similarly, so if you have 0 0 0 0, it will be minus 3 in BCD. Is it feasible? I hope your doubt is clear, right? So input XS3 0 0 0 0 is not valid. Input should be 0 0 0 0, but that input is not valid input. Okay? Okay, thank you. Input should be started from definitely 0 0 0 0, because is the, if you are doing for the 16 combination, you have to put the 0 0 0 0 cell here, na, and you have to put something in the K map also. As this number is not valid, that's why we are putting cross. Similarly, similarly, if you go for B, you can see where the ones are there. You have from 7, 0, 111 is 7. So 7 is 8, 9, 10. Okay, thank you. 7, 8, 9, 10, definitely we will be putting 1 for K-map B, and similarly we will be putting crosses for the rest 6 condition that I mentioned, M0, M1, M2 and M13, M14 and M15. So let's see this one. So same crosses are there, here crosses are there, 6 crosses. Apart from that, we are putting the values of what? We have 7, 8, 9 and 10. So you can make what? You can make a quad out of this. Okay, you can make a pair out of this, and from the 4 corner points you can make another quad. Is it clear to you? So definitely if it is a pair, so you are having this value x, y, z, because this is the yz part and the common is here 1, 1 means x. Okay. Similarly, if you see the folded part, this first row and the last row, the common term is what? 0, 0. 0, 0 means y bar. So this y bar, and what is the common between these two rows is basically x bar. So this is x bar, y bar for this overlapping part. Okay. Now, and if you consider the 4 corners, you will be getting what? You will be getting the horizontal common part will be 0, 0, that is x bar. And what is the vertical common part? বুঝতে পারছিস তো? এই 4 corner হলে you will be getting the horizontal common part x bar, and the vertical is this column and this column, that is 0, 0. Okay, 0, 0 means z here, so z bar. So one term I missed out, it should be x bar, z bar. Okay. This part you are having problem. Okay, I'm just removing this one. What I was telling, that for 0, 1, 2, then you have the 13, 14, 15, we have put the crosses, fine. And if you see the column of B, you can see here for which you are getting 1, for 7 you are getting 1, for 8 you are getting 1, for 9 you are getting 1, and for 10 you are getting 1. So 7, 8, 9, 10 you will be placing 1 in the K-map. So let's see what we have done. So where is the 7? 0, 1, 2, 3, 4, 5, 6, 7. So 7 we are putting 1 here, then 8, then 9, then 10 this side, 11 is not mentioned, then 13, 14 and 15, both all these are cross values, and this 0, 1, 2, all these are cross values. Okay. So now how you are going to do it? You can take this one, this portion and this portion, you can be combining together by overlapping method. You can combine these 2 sections to make one quad, right? So what if you want to make the quad out of this? So what is the horizontal portion common? that এগুলো করবি, প্র্যাকটিস করবি, না হলে সব ভুলে যাবি. So it will be 0, 0 means what? It will be x bar, this portion. Okay, x bar. And what is the common in between these two? This 0, 0, that is y bar. So this is what? Done. Now how many ones are left? So these two I can make a pair, right? So what is the vertical common part? Both the thing will be there. So both the thing means yz. So yz I have this vertical common part, and for this two what is the horizontal common part? This 1, 1. This 1, 1 means x. So this is the horizontal and this is the vertical part. Done. And if you see this way, this 4 sectional corners, 4 corners, because other ones are there, so 4 corners will make horizontally common which part? It will be 0, right? 0 means x bar. So that part I missed out, here should be x bar. And for this column and this column, what is the common thing? that is also 0, that is Z bar. I think it is clear to you, right? It's raining heavily here, so maybe sometime we will be disconnected, so it's heavily raining here. Anyways, so this is about the B. Now let's see the C. C is basically, you can see here, this is for 0 1 0 1 is 5, right? So for 0 1 0 1 is a 5, so 5 6, then you have 1 0 0 1 is what? So 9 and 10. Okay. For B in the box 15, there should be not be 1. 1 is not there, right? Its cross is there. This is a 15. So it is 15. So its cross is there. 1 is not there. Please check once. Okay. Now when we are talking about C, we will be placing these values. Na bujhte parle bolbi. When we will be placing the values, that is the 0 1 0 1 0 1 0 1 is 5 6 for 5 and 6, and you have this 9 and 10. Okay, so let's see here. What is 5? The 0 1 2 3 4 5. So this is 5, this is 6, then 8, this is 9. Okay, and this is 10. So 5 6 9 10 we are putting values 1, and other 0 1, this is 2, and this is 13 14 15 we are putting crosses. Okay, so you can see, you can just accommodate the crosses and you can make one quad out of this, and you can make also another quad out of this. So you will be getting for this value all the terms that are vertically common, all the terms, no horizontal common part. So we will be having this is y bar z. Okay, y bar z, and for this it will be y z bar. So it will be simply y or z, right? So this is the way we will be doing. And the last one I will be telling you, for D value, check where the ones are there. So this is for 0, that is for 3 you have, this is for 4 you have 1, 6, okay, then you have 8, then you have 10. Okay, so this is the way we will be writing, and you have another one for 12. So let's see here. So all the places whether you have placed the 1, so you have 4 6, you have 8, you have 10, and you have 12. Rest 6 crosses we are putting here. Okay, so the folding method, you know, you can you just make one octet out of it. Okay, and you know all the horizontal rows are different, only you have to take the vertical part common. So what is the 0 0 is common? So what is this value? It should be 0 means what? This z value, right? So 0 means z bar will be there. So this circuit is going to be a very big circuit. Okay, I am taking I will give you time. So it's not like that 3 things you have to do by one day. If you take required time, you can take time, but please try to do it by yourself, and please do not upload junk files, because some discrete math files also I am getting here. Okay, please do not do that. At least if you are capable of doing one part of the circuit A, please try to implement only the part of the circuit. You please write it down, ma'am, I am only able to do that one. Fine, please do not upload junk files. Okay, those which is required only please upload those part. Okay, now see, this is the circuit diagram. You can do it very minutely. Shovik in the morning, Shovik have shown me one circuit that is very good. Anyways, so what we have done, we will be using the 4 input here, 3 4, that is the XS3 input, and we will be getting the output of this value like ABCD. You can write down ABCD. This is the MSB, and you can say this is the LSB. Okay, ABCD you can write down. So what I have shown you here, I will be showing the circuit diagram also. So this is the C and this is the D. So when we are writing this way, so this circuit you can see, if you see the value of A, if you remember the equation, what was the equation of A? Equation of A was Wx plus Wyz, right? That was the equation you obtained. So when you have obtained this equation, what we are doing here, this product term, I hope you have cleared this confusion. So if you have a 3 value in the product term, we will be sending the W value, and then we are sending the Y value to this one. So we are getting the WY, and the last is, so this is W X, Y and Z. So the Z value I am putting to another AND gate. Okay, so this is the Z. So you are getting here W, Y, Z. Okay, this is one part of the summation is done. Now the second part, you have to do the Wx part. How you are going to do the Wx? I am just taken this point from this line. So it is the W value that is coming here, and this is the value of X. I think this one line. Okay, if you see this one, so this is the X, and if you just put this one, it will be Wx. So if you add this one through one OR gate, you will be getting the value of A. So the circuit is going to be a bit complicated, so we can just check in the Proteus how it will look like. Okay, so here what I have shown you, that please try to understand. Here what is the value? I have taken the first value, or whatever the value you can take. So if you put 0 0 1 1, that is 3 in XS3, so BCD will be 3 less, right? So BCD is 3 less means it will be, see, you can see all the blue dots, blue and this 4 blue dot, that is 0 0 0 0. So XS3 is 0 0 1 1, that means the BCD will be 0 0 0 0. Right. If you check the second example, so all the examples I am just doing for the XS3 to BCD converter. Okay. So this is the first example I have given. I have given the value 0 0 1 1, and I have obtained the value 0 0 0 0. That is correct value. One of the example I have taken, right? I can take another value as per my wish. Suppose I am taking another value. So what is the value of this one? This is 4. You can find it. This is the W, X, Y, Z. So it is blue, red, 0 0. That is, it is 0 1 0 0. I have taken the value. So what will be the value of? You can see the truth table. So this will be 0 0 0 1. So actually you are giving 4 and you are getting 1, right? So 1 plus 3 equal to 4. Anyway, so you can do this one, 2 3 examples. So in the observation table part, you will be writing this one. Okay, if you want to check the output, you will be just checking. I am just you can show, this is the Proteus part, we can just simulate. Okay, you can just make the circuit diagram. I think it is visible to you, right? Do you have any doubt up to this? I hope it is not. So we can start SVM. Okay, the attendance link is already open, so you can give the attendance by 4. Okay, because we need to submit the attendance part. Please give the attendance, it will not take too much of time, in between 3 to 3:10, not now. So start SVM I have done, then I am doing the start simulation. Okay, So this is the value. So I have taken 0 1 0 1, that is 5. 0 1 0 1 is 5. So if you are doing 0 1 0 1 as 5, so what you are supposed to do, or output, you are supposed to get the output 5 minus 3 will be 2. So 0 0 1 0 you are supposed to get, right? So if you are giving 0 1 0 1, you can check the truth table here. If you are giving 0 0 1 0 1, 0 0 1 0 you are supposed to get. 0 1 0 1 you are giving, you are getting 0 0 1 0. Let's see whether you are getting 0 1 0 1. You are giving 0 0 1 0 you are getting. So it's correct. You are getting the correct output, right? So you can check anything. So I can check this last portion, that is 12. So just wait. So I can check 12 means 1 1 0 0. What you are getting, going to get 12 minus 3 9. That is 1 0 0 1 you are supposed to get. So this is red 1, blue 0, blue 0, and then red is 1. So when you are doing 1 1 0 0, that is 12. 12 minus 3 will be the BCD, that is 1 0 0 1. You can check 1 0 0 1 is coming or not. So this is the way you can simply do it, but please make sure one thing, that the connections you are doing is correct or not. And the way I told you, if it is a product of 3 variable, you just divide that thing into 2 variable. Whatever you are the output getting here, you will be applying to the second AND gate, and the third variable also you will be applying to the second AND gate. So you will be getting the final product of 3 variable from this end. This is the way you will be breaking the 3 variable into using the 2 AND gates, right? Now, so this is the thing we have done. Now let's come to the our main objective, that is the next part of our task, that is experiment number 15. Now in experiment number 15 we will be talking about, you see, experiment number 15 will be telling you about the multiplexer part, and 16 will be telling you about the demultiplexer part. We will be doing a smaller circuit, so we will be taking 4:1 marks. You can create a 8:1, 16:1, that will be a big circuit, right? So apart from doing that, we will be going for the simple 4:1 multiplexer. Let's go through the thing. Here also, to implement the circuit, you will be requiring the AND OR. This 4081 is the AND, 4071 is the OR, and 4069 is the NOT gate. Now, so what do you mean by multiplexer? I hope you have studied this one in the COA theory, lab, and in your class also. So multiplexer basically is a device. It is not working. It should be working, right? Just wait. Okay, sorry. Okay, thank you for reminding. So lots of things are going on parallelly. I have not plus please do it between 3 and 3:10. Okay, so what I was discussing about the multiplexer, we will be dealing with the 4:1 marks. Okay, so multiplexer is very important. If I am going through the COA theory, this multiplexer is multiple times used in the multiplexer and decoder concept is very important if you go through the theory of COA. Okay, so that's why I thought of discussing this one. So multiplexer is what? Actually multiplexer is a circuit which is going to convert many into one. In short, many to one. Multiplexer means many to one. In short, we can write. Okay, You can write it like we can write this one as many to 1. So that means you must have one circuit where you are giving 1, 2, 3, 4, suppose 2 to the power n number of inputs, and you are getting how many outputs? 1 output. Okay, so this many number of inputs you are giving and you are getting 1 output. Now there is a concept of select line. So how many select line will be there? There will be n number of n select lines. Okay, now you may ask me, ma'am, why it is used? Because when we will be using the COA addressing different you can memory organization, you have already studied, right? So we are using the memory organization and we are fetching the operands from the memory, right? So from where have you thought of how many suppose this type of concept is used. So when you are using the memory organization, this type of thing will be required. I will be coming to that part later. So this select line concept is required here. Okay, and this multiplexer is known as the data selector. This is very important. Now what is the structure? As I have already told you, the structure is like this. There will be this many number of inputs like 1, 2, 3, 4 up to 2 to the power n number of inputs, and there will be n number of select lines, right? So when you are designing 4:1 mux, in short we write it as mux. So 2 to the power n will be what? 4. That means n equal to 2. So when you are using 4:1 mux, how many select lines do you require? You will be requiring 2 select lines. Okay, you will be requiring 2 select lines when you are designing 4:1 mux. Apart from this 4:1 mux, there is different types of mux, like you have this 8:1 mux, you have 16:1 mux. Okay, so depending on this, actually the number of input increases. Okay, and definitely the select line also, number of select line also increases, right? Now we will be talking about in the laboratory part only with the 4:1 mux. So when we are talking about 4:1 mux, I have told you 4 lines will be there at the input. So there will be 4 input lines, right? That means I told you 2 to the power 2, that is 2 to the power n. So n is what? 2. That means there will be how many number of select lines? 2 select lines. Why I am telling multiple times? Because this is the first time you may be reading this one. That's why I am telling this one. So 4:1. This 4:1 means what? There will be 4 inputs. There will be y1. There will be 1 output. That is this y. Okay. So you are getting the output from this n, that is y. Okay. So this is the block diagram. Now what is y? How you are going to calculate y in terms of I0, I1, I2, I3 and S0, S1? So definitely there should be some combinational circuit that is residing within this black box, right? So we have to find what is the circuit there in this box that is going to channelize the one data. That is, suppose if we are making the select line, I am just erasing this part. Suppose how the select lines are working. When you are, suppose you are giving a data 1 0 0 1. This is the data suppose you are giving. Yeah, I3 you are giving 1, I2 you are giving 0, I1 you are giving 0, and I0 you are giving 1. So when you are selecting, putting a 0 0 here, can you tell me what is going to be the output? You have studied already, right? So you have done memory organization, you have done the lab part, COA and all these things sir has already told you. You are giving 1 0 0 in the 4 inputs of the multiplexer, because you have to validate this one, what you are going to get at the output. So you see, when the 0 0 is selected, only which value is going to be passed through this? There are 4 values that are coming. So which value is going to be passed? That is the I0 is going to be passed. So if you are giving 0 here, you have to get this 0 as 1. Definitely. Very good. Very good. I0. Okay. Now similarly, if you go through this, if you make the select line as suppose 0 1, then which value is going to be here? I1. If you are making this one 1 0, which value is going to be here? I2. Okay. If the select line is becoming 1 1, which value is going to be here? I3. So depending, suppose it is not a single line, in normal telecommunication system where we use a huge multiplexer and digital multiplexers are used, okay, and you have the concept of FDM, TDM, and nowadays OFDM, CDM, all CDMA rather, multiplexing, multiple access. So all these things, actually the concept is many to one, okay. Now multiplexing access is a different concept. WDM, in optics we will be using the wavelength division multiplexing. So here multiple wavelengths are there, and like a prism it is going to select only one. So output of the prism will pass, that is going to pass a single wavelength. You are giving the lambda 1 2 3 4 5 6, and at the output, that is the concept of WDM, wavelength division multiplexing in optical. Nowadays the processors are using not only the electrical components, right, they are using optical gates. The fast processing, like you are using like GPUs, right? So where will you use this type of 8085, 8086? No, absolute no. We will be using some, suppose you are using supercomputers, will you use this type of low speed data units or low speed CPUs? We will be using GPUs, where very fast processing. Optical computing nowadays is a recent research topic, okay. So anyways, apart from this we will be discussing in some other days. So this value you will be getting here. So let's see the truth table part. So when you are giving the select line as S0, S1 and S0. So S1, S0, what I was telling, depending on the values, the output Y is going to be selected, okay. So when you are using 0 0, the output is going to be I0. Oof. Just wait for 1 minute. one thing you can do, you can actually simulate that part. So we will be starting the again, just wait. Meanwhile you can simulate the every day the same issue. Oof. Just wait for 2 minutes. Okay, so let's start with the topic. Yes, I was discussing, yes, the last date of submission is basically today. For these 3 experiments, okay, first 3. Now in this the truth table I was discussing about, and unfortunately it was stuck in between. So the truth table shows that there will be 2 select lines, S1 and S0, and depending on the values of this S1 and S0 we are getting the outputs like I0 or I1 or I2 or I3 at the output Y. Okay, so this is the thing. Now in this case it is important to mention that in this connection what is going to be the equation of this Y in terms of the S0, S1 and the other outputs. Okay, so we can check here that this I0 is coming at the output when the inputs are 0 0. So how we can tell this way, or how the equation is coming? Actually if you put this values S1 S0 as 0 0 here, we can find that if you put 0 0 here in the equation, what you are supposed to get, if you put 0, S is S0 or S1 is 0 0, so this value is going to become I am putting this value in the equation, okay, Y. So what is Y? So this value is going to be 0, this value is going to be 0 and this value is going to be 0. Why? This S0 S1 both are 0 0, that's why it is going to be 0. This S0 S1 is 0 and it may be 1, so it is going to be 0, and here S0 is 0, so this is going to be 0. So in this case we can find out that if you are putting the combination 0 0, the Y output is going to be 0, right? So similarly you can take error combination like S1 is 0 and S0 is 1. You can put and you can check here what is going to happen. You will be checking this, sorry, this one I wrongly written, this 0 plus actually it will be 1 into 1 into when I was talking about 0 0, so what I was telling, that when you are putting the 0 0 value, you will be getting the y equal to I0. You got it? Why I am telling this one? This value is going to be 0, this value is going to be 0, and this value is going to be 0, as you are putting 0 0 here. So why you are getting what? It will be just 1 into I0. So that's why you can say here that y equal to I0. This is the first case. Okay, you need to submit this one by today. Okay, if you are unable, then it will be late submission. At least try to submit one of the 3 experiments, which, because the first experiment circuit will be huge, right? So this one. So now if I talk about the reverse thing, that is another take another condition, like it, you can take the S1 equal to 0 and S0 equal to 1. If you take the second condition as S1 equal to 0 and S0 equal to 1, you can put it here. So S0 equal to 1 means this value is going to be 0 here. Okay, sorry. কি যে প্রবলেম হয় ভগবান জানে, বিরক্তি করে। So when you are putting this value is not going to be 0, because S0 is so when you are putting S0 equal to 1, this value is going to be 1 here, and this value is going to be 1 here also. Okay, so the remaining part is going to be, you can check it, that this S1 equal to 0, that means this value is going to be 0. Then this S1 equal to 0 means this value is going to be 0. Okay, and you will be getting this value because S0 equal to 1, so S0 bar will be 0, that's why the whole thing is going to be 0. So only you will be getting this one. So when you are putting this combination, you will be getting y equal to I1. Try to submit this one by today. If you are unable, then the submission date will be extended, no problem. Try to do it how much it is feasible. Okay, so this is the circuit diagram for this S0 S1 will be this. Now you will be giving the 3 inputs, rather 4 inputs, I0, I1, I2, I3, like the equation. So you are just implementing the equation which you have studied in here. Okay, so you will be using this one through 1 AND gate. You can use 3 input AND gate also if you want. Yes, definitely I will share the PPT in the classroom. Okay, and this will be another input, so you require another AND gate if you are using 3 input. And if you are using 2 input AND gate, like the way we have done in the Proteus, you will be using for this product 1 AND gate, and for this product you require another AND gate. So for this whole thing you will be requiring 2 AND gates. For this also you will be requiring 2 AND gates, for this 2 AND gates, and for this 2 AND gates. And you also require the OR gates. For how many OR gates will be required? You will be required, you have to check that one. For this I think 3 OR gates will be required, and you require the NOT gate also, because S0 bar and S1 bar, both the things will be done. Okay, so take 10 minutes of break, and I will be starting the demultiplexer in the next 3:10. Okay, take 10 minutes of break. So, or you can implement the circuit if you want. So this is the circuit diagram. So if you want to break this part, you can just rewrite this one also. So this 3 input can be broken into this way. So it can be S1. So suppose I can just represent this one in this form, S1 S0, and this output is going to be here through 1 AND gate. So this is basically I3. So instead of 3 input, so instead of So I will be starting by 3:10. Just take 2 minutes of 10 minutes of break. I will be starting the session by 3:10. Okay. Okay, so it's 3:09, so I will be starting the session by 3:10, and just wait for 1 minute. Okay, so we are back, so the break is over, so let's start the thing once again. I hope there is no lagging in the video and audio, right? Okay, so we have discussed this one. So this is the circuit diagram for this, and if I want to go to the next part, we can see this is the simulation part of the 4:1 multiplexer. Okay, so in the simulation part we can see here that we have checked the two select lines here. What are the select lines? I have discussed. The select lines were S1 and S0, and I have taken two NOT gates so that you can just put the lines like you have done the first year, the experiments, the theoretical part, the way you have designed the circuit. And this is basically the way you can write. This is I am just taking I3, I2, I1 and I0, whatever the way you can think of. Okay, so when or the reverse thing, I think this is I0, I1. In my case I have taken this way. You can check this one. So when we are putting S1, so both are basically blue, right? So this means that it is 0 also, and this is also 0. Okay, so if both the inputs are 0 0, if both the inputs are 0 0, then what is going to happen? Can you tell me what is going to happen? Basically this I0 value is going to get or to be reflected at the output Y, right? So you can see I have given red, that's why you are getting 1 here. So you are giving I0 as 1 and you are getting the I0 value here at the output. Okay, let's see, is it understandable or not? Shall I repeat this once again? I have taken this S1 value and S0 value as 0 0, that's why both are blue. Okay, I pass this one normal line and NOT gate, pass through the NOT gate. So to get this one will be basically S1 bar, right? So this will be S0 bar. So the I0 value in this side I have taken, so I have replaced the 3 input gate with the 2 input gate. That is the thing I told you in the last case. Okay, and you can check here what the thing I told you. This is replaced by this one. So each of the 3 input gate will be replaced by this 2 AND gates, and this big OR gate is replaced by this type of circuit diagram. Okay, now you check this one. So that's why this I0 is coming at the output. Okay, now I have taken the next thing. So this is going to be what? You are putting this one S1 as 0, S0 as 1. Okay, so what you are going to get? which value, which input you are going to get? You are going to get I1. I1 I am putting here 1, that's why at the output I am getting 1 here. Okay, if you are connecting, if you are getting some wrong output, please try to, that is a simulation problem. Please do not simulate the whole thing at the same time. See, one thing, when you are doing the XS3 to BCD conversion, you can just check, you can make the circuit for A, you can make the circuit for B, you can make the circuit for C and D. C and D is very easy, you just XOR gate and some complement is required, but AB circuits are huge. So you do the circuit of A and you just simulate that one and check whether the output is coming or not. Otherwise, when you are making a big circuit, it is very difficult to debug. Otherwise, you check the debug button, click it and check whether some color combination, when we are debugging something, you can see from the debug section that all the inputs are having some small boxes with colors. Okay, if some gray color is coming, that means you have some connection problem definitely at that point of input. Please check that one. Otherwise I have to check minutely for each of the circuit diagram. Okay, it's better to get the output one by one. Okay, now if you see the next one, I have selected this one as S1 as 1, S0 as 0. So you are getting this option as this one, S1 as 1 and S0 as 0. So it is the which input is going to be selected. This is I2, right? This is I2 is going to be here. So if it is 1, you are going to get 1 here. So at the Y you are getting I2. And the last snapshot that I have taken, that both the cases when both S1 and S0 are then whatever the fourth output, that is I3, that you are going to get here. So it is red 1, so you are getting the output here. So depending on the select line, you can check. So you can check when you are making this one 1 1, you can check, you can put on and off any of the button, that is hardly going to reflect at the output. The way you can also check. Okay, few of you have sent me some circuits, so I have to check one by one where the fault is. Otherwise there may be some shorting problem, you have to check that one. এইটা আচ্ছা আমি বলছি একটা একটা করে। Okay, so you have to write the observation and conclusion if you want. Now come to the demultiplexer, because we need to complete this one also. So when you are going to implement the demultiplexer, actually you have to implement this one using the same way, the way you have used the multiplexer. Okay, so in case of demultiplexer, actually it is one to many, the concept is one to many. Okay, so in one to many concept, what we can find, let's see. So it is basically a circuit which is having a single input line. We know this one single input line, and you have several digital output lines. So what is the relation? We know 1 is to 2 to the power n, right? So when we are talking about the demux, the box you can just visualize like this. So you have one input and you have multiple outputs, so the number of outputs will be 2 to the power n. Okay, and the number of select line will be n. So one inputs will be there, one input will be there, and 2 to the power n output will be there. Okay, so this is the thing. So this is the block diagram, you can see This is, I have just taken it from this website, and you can check that this is working as the data selector. So depending on the values of the select lines, that input, which input or which data is to be channelized, that is going to be decided by which control signal, that is the select lines. Okay, so if this is going to happen, you can check the truth table of this. You can check here the data select line. If 0 0, then which the data will be channelized through y0. When the data select line is 0 1, the data is channelized to y1. When the data select line is 1 0, the data is channelized to y2, and when the data select line is basically 1 1, this is channelized to y3. Okay, now here can you tell me how many outputs are there? For each output, you know, one equation will be generated. Okay, so when you are going through this, you will just can say this one, that for y output, this data will come when you have the input equation S10 bar, S0 bar and D. Okay, you can put it the 0 0 value. So this value y0 will be what? When you are putting 0 0 condition, when you are putting 0 0 condition here, just put the 0 0 when S0 equal to 1 and S1 equal to 1, sorry, S0 equal to 0 and S1 equal to 0. You can put those two conditions here, and you will be getting y0 equal to 0 bar dot 0 bar dot D, right? So that is 1 dot 1 dot D equal to D. So you will be getting y0 equal to D if the select lines are 0 0. Got it? Similarly, if you check for y1, then the select line should be 0 1. For y2, the select line will be 1 0. For y3, the select line will be 1 1. Okay, so this is the way you will be writing the equations, and you will be creating the 4 small circuits. And you can see only 2 AND gate and 2 NOT gates are there. So very simple circuit. Okay, for each of the case. Now we have selected, so what are the inputs you can find? D should be one input line, S0 will be one input line, and S1 will be one input line, and both the bars will be there. Okay, so let's see here what is the circuit we have drawn. So this is the line, basically I have taken this as D line. This is the D line I have taken, and maybe this is S1 and S0 line. So you can do it, this line is showing you the S1 bar, okay, S1 bar, and this line is showing you the S0 bar. So these are the 2 lines, vertical line I have created through this, and these 2 lines are basically the S1 and S0. Now for this case, this is the thing, output is will be what? Output is going to be when it is 0 0 and D equal to 1, you can see that data 1 is coming here. So this is basically the first one, that is, you can check the last equation. This is the y0. Y0 you have implemented through this part. Okay, so you can say this is basically the y0 you are getting at the output. This is the y1, this is the y2, this is the y3, right? And you can check whatever the data is, that will be passed through the output depending on the values of the select line. So if it is 0 1, let's see, if it is 0 1, so here what I have done, same thing, this is the data, this is the S1 and this is the S0. So I have taken what value, which value we have taken S1 as 0 and S0 as 1. So you can say which output value we are going to get. Here the 1 we are going to get definitely, but in which output? Here, 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 or here? Where? Definitely it will be channelized to the second one, right? So second one was the equation you can see here just 2 slides before. The y1 is the second one, so it is S0 S1 bar D. Okay, so this is the circuit for S0 S1 bar D. You can check where we have tapped from this, so be careful while tapping, otherwise the equation is going to be distorted and definitely the outputs you are getting will be distorted. Okay, so be careful. So these circuits are smaller circuits, you can just simulate that one 1:4 marks or demarks, but that XS3 is a comparatively bigger circuit. I request all of you to do one thing. You just do for XS3 to BCD, make the A portion first, check the column of A, then make the B portion of the circuit, then check the column of B in the truth table, like that only. Otherwise if you do the full circuit at the same time, it is very difficult to debug. For yourself I am telling, okay, it is for yourself. Now this is the way we are actually doing, and the last thing will be there. So this is the 1-0 portion, same thing. So definitely D is this one, and this is the S1 equal to 1 and S0 equal to 0. So the third in output we are getting here. So this is the Y2, we are getting 1. We have given the data, whatever we have given, we are getting it here. Okay, and the last one is when both the S1 and S0 are 1 1. So if the data is 1, here the S1 equal to 1 and the S0 is also 1. So in that case we will be having the output at the Y3. Okay, so you can check the simulation. Observation part is the same as truth table. Okay, so before going through this, we will be just checking the Proteus part once again. So I will be telling you first the 4:1 marks. You can simulate parallelly, it will be easier for you, because the circuit for 4:1 and 1:4 is not too much complicated, whereas the XS3 to BCD is a very complicated circuit. So this is the circuit part of this. I can minimize this one and I can drag it as per my convenience. Okay, so this is the circuit diagram for 4:1 multiplexer. I can just start debugging and I can just run simulation. Okay, somebody is asking why should be 1. Okay, if the answer is not correct, please make sure that you have done something difficult, because from my end it is very difficult to understand where is the problem. Okay, see, when we are see one thing, when you are debugging the circuit diagram, okay, so when you are using this one, you should debug first. So when you are start SVM, that is going to debug the circuit. Please note one point, I am telling you because I am magnifying. See, for every gate you have this colored output, okay, colored input. So after the simulation all the gate input output should be colored. If you want you can magnify the circuit diagram and you can check it. Otherwise sometime we just what is the error, we are neglecting that part and we are just going through the circuit and we are just running the simulation, that running the run part, okay, but that ultimately does not solving our problem because we have neglected some of the parts. Maybe if the color is grayish, that means that part is not correct. So you have to just right click and then you can just right click and then you just remove that part if you want. Okay, so I'm just minimizing once and I'm just showing the result if you are doing also with me. So you can just run the simulation part and you can check the values. So if it is 0 0, okay, then the I0 is going to be here at the output, and you can check at this point if you just change the values of any of this, it is not going to be changed, okay, but if you are making this one 0, it is going to be 0. Okay, so depending on whatever the input you are giving here, that is going to be at the output. Why this is happening? Because you have done the select line of 4:1 marks as 0 0. Okay, I will be checking, just wait for 2 minutes. Okay, and similarly if you just check it for 0 1, you will be getting which value here, whatever the values you are giving for I1, that is going to be reflected at the output. So it is going to work as the data selector of which input, the second input that you are giving, whatever the data you are giving, that is going to be channelized at the output. Similarly if you make the select line 1 0, the third input whatever you are giving, that is going to the output. Okay, and the last part I am telling you, if you are giving 1 1 at the select lines, the fourth input whatever you are giving, that is going to be reflected at the output. So this is the scenario in case of the 4:1 multiplexer. Okay, and if you go for 1:4 demultiplexer, so definitely if I tell you that you just create a circuit for 8:1 multiplexer, you can understand the circuit will be huge, right? So how many select lines will be there if I tell you to make 8:1 marks? In exam we can give, right? And if you do it, so for that you require 3 select lines, and definitely the equation will be very big, right? So definitely the first will be 3 select line, means you have the first term y will be y equal to s0 bar plus s0 bar, s1 bar, s2 bar into y0 plus, like that it will be a huge term. So 8 terms will be there, and each product term will contain 4 things, right? So this is the way you will be designing. In theory you will be studying all these things. Okay, so let's do another simulation which I have already simulated. So that is the 1:4 demarks. Whether right or wrong, you can actually understand if you just take the all possible outputs. Okay, you can find whether it is working or not. So validate the truth table for all the input combination. Otherwise do not do haphazardly, take your time and do it step by step. Yes, Shobhik, I will be checking your circuit diagram. Just wait, let me complete this part. Okay, so this is the, hope you can see this one. This is the 1:4 demarks, and we can just have this data select line 1, select line 0, and the 4 outputs. So we know have the 1 data input and you have the 4, 1:4. So you can check the start SVM, and you can just do the run simulation part also. Okay, so when you are doing the run simulation part, you can just find, so if it is 0 0, okay, 0 0, then this output is going to be this input is going to channelize to this output, okay, the first output. If you make this 0 1, this input is channelized to second output. If you make this select line 1 0, this input is channelized to third output. If you make this 1 1, this input is channelized to fourth output. Is it clear to you? You can validate this one. Okay, so this is the way actually, otherwise it is very difficult. Just wait, I am checking the circuit and I am letting you know. See, there is no concept of 2:4 demarks. 2:4 decoder will be there, but 2:4 demarks is not there. So there is a difference between decoder and demarks. I will be telling you, don't get confused. Decoder, in case of decoder, there is no select line, whereas in case of demultiplexer, there will be n number of select line if there are 2 to the power n number of outputs. Don't get confused. Demultiplexer, there is no concept of 2 to the power 4. 2 to the power 4, you are just telling, that is decoder concept. 2:4 decoder is feasible. Okay. Is it clear to you, Shobik? So you can check this one. Okay. Now let's come back to the theory part again. So this will be, we will be starting another part, that is I will be sharing you the PPT in the group. Okay, so the experiment number 15 16 both are 4:1 marks and 1:4 demarks. Experiment 10 is XS3 to BCD, and now we are going to experiment number 17, that is 2:4 decoder. This is the small thing, it's not take too much of time, you can just easily do it. Now you can check this one, 2:4. This is the decoder circuit is many input to many output. In case of demultiplexer, what I told, many or multiplexer, many input to one output. It's not many to many, right? It is either many to one or one to many, but here many to many will be there. Okay, so don't get confused. So decoding, memory decoding part, you have used the decoder. How will you get that address? Okay, fine. So this is the diagram of the decoder. So n number of inputs will be there, and there will be 2 to the power n number of outputs. It's not n:1 or 1:n. N is to 2 to the power n. That is the format. So what can be the scenarios? It can, or how many types of encoder that might come up in the theory, you may learn this one. So there are different types of encoder. I can say the shortest one, suppose n equal to 2. So suppose if n equal to 2 I can consider, then what is going to happen? It will be 2:4, right? It will lead to 2:4 decoder. Okay, when n equal to 3 we consider, so here 3 input, that means here 2 to the power 3 will be there. Are you getting me? If 3 is there, because it is 2 to 2, that is the n is 2 to the power n format. Okay, so if it is 3, then it is 2 to the power 3, that is 8. 3:8 decoder, that is you will be learning in the theory also. Okay, now there are different application of decoder. Decoders can be used in counters also. Okay, and they are also used in the analog to digital converters also. Okay, and the decoder output can be used to drive the display. 7 segment display, NB sir was telling you 7 segment display. You can drive the BCD to 7 segment display to by through some decoder. So BCD to 7 segment decoder driving the LCD. Okay, so this is happening. It is very much useful, and everywhere when we are using the COA architecture, all these things, we will be using this decoder circuit very frequently. Okay, so this is the simplest form of this. So this is basically the n. This 2 to 4 means this is the n, and this is the 2 to the power n. Okay, so this is how many inputs are there. This is enable is used for the chip select line. You can say the chip select line. We are not using it here, but in hardware circuits we have to put this enable equal to 1, then only this will be working. So it can be there will be 4 combinations. So for each of the combination, that particular output is going to be activated. Okay, now if you see this one, so what I was telling, these 2 are basically the input lines, and these 4 are basically what? The 4 output lines. So depending, so first combination will be 0 0. If it is 0 0, this D0 value will be updated, or this value will be activated. If it is 0 1, then you have this D1. If it is 1 0, then it will be D2, and if it is 1 1, then it will be D3. So this is the way actually we will be getting the truth table of 2:4. Can you tell me how it will be for 3:4 3:8 decoder? Can you tell me, can anyone just tell me how it will be for 3:8? How many inputs will be there? Then definitely A2 it will become like you have the 3:8. If I talk about, it will be 3 inputs, right? So like A2, A1 and A0, and in this side you will be having how many? From D7 to D6 like D0. So there will be 3 input and there will be 8 outputs. Right? Okay. So what will be the equation for this? For this we will be getting the D0 equal to 1. Yes, there will be 8 outputs. 8 out. Why 27 input? 2 to the power 3, that is 8 possible inputs will be there, right? So if you have 2 input bits, so 2 to the power 2, 4 possible inputs we are finding here. Right? There are 2 input, then 2 to the power 2, 4 possible input. If 3 inputs would have been there, if 3 inputs would have been there, the কতগুলো হবে? 0 0 0 2 1 1 1. For that every case, for 0 0 0 D0 will be activated. For 0 0 1 D1 will be activated. For 1 1 1 D7 will be activated. Right? It's not 27 input. It will be just 8 input combination will be there, and for each case that particular data output will be activated. Yes, 8 outputs. Now, so this is the, I'm just removing this equation. So this will be the equation for very simple and very small circuit, but if it is 3:8 decoder, it will be a larger circuit. So you will be having this one when it is going to be 1, when both are 0 0, that's why A1 bar dot A0 bar. This column will be 1 when it is going to be 1, otherwise there are zeros, right? Only in this position it is 1. So that's the way we convert the truth table into equation. Same way we are doing. D1 will be 1 when it is 0 1, that is A1 bar A0. Okay, similarly for the other 2 cases. Okay, if it is not coming the full part, please just you have to do it again. Okay, otherwise there is no secondary option. it happens to me also. It's not like that I can do all in one chance. So it happens, so when you are going for the examination, you have to do it, right? So at that point you do one step and then you check the truth table of that part only. Okay, suppose in this case, suppose will you do it the whole thing? No, I will make sure that D0 is at least coming. At least I will be doing the circuit for D0. I will check whether it is coming or not, because the truth table is small, and then I will check for D1, then D2, then D3. One, I will do it a partial part, that is the every time I will not write the full code and I will debug. Okay, that is the problem. In MATLAB we used to do it easily, but in C that is not going to happen. But here we can do it, right? So in Proteus or you can Circuitverse, you can do it. You can do a partial part and you can check whether the output is coming or not. So otherwise, if you do the full thing and that something is not coming, that is very problematic for you. Okay. So this is the circuit diagram. This is also I have taken from the website. So at least it's not case of 3 input AND gate. So 2 input AND gates are there. So easily you can implement this one, and the circuit is also very small. Okay. So this is the diagram I have taken. So I have taken this one for this. So what are the values you can consider? So this is the value A1 and A0 I have considered. Okay. So this is the A1 and this is the A0. So if the A1 is 0 and A0 is also 0, you can see that this is 1. So this is basically D equal to 1. Okay. So I should not say D, because D0 I should say, right? So I should say here D0 instead of D. So it is the D0, D1, D2 and D3. Okay. So if the values of this A1 and A0 is going to be varied, it is 0 1 combination of A1 A0, then you will see that it will be D1, right? It's not D, it will be D1 is going to be activated. Okay, if it is A1 A0 combination is 0 1. Now in the second case, third case, if it is 1 0, if it is 1 0, then the third one D2 will be activated, and the last one, if both the A1 A0 both are 1 1, then last one will be activated, that is D3 will be activated. Okay. So this is the case. So we can check this one. We can check this one in the Proteus also. So this is the 2:4 decoder. I request all of you to give the attendance. Okay, do it fast. I request all of you to give the attendance. So this is all about today, and I will be discussing about the 4:2 encoder and all other part in the next class. Okay. So we can check here the 2:4 decoder. We can start SVM. And we can do the run simulation part also. Okay, now we can check here. If it is 0 0, then definitely this D0 value will be 1. If A1 A0 is 0 1, then D2 value is going to be 1. If this A1 is 1, A0 is 0, then D3 value is going to be 1. And if A1 is 1, A0 is 0, both the values are 1, then the last one D3 is going to be 1. So this is the way you can simulate the 2:4 decoder. Now you can do the assignment in your home. This is not to be submitted, but you can just check it. You can do this 3:8 decoder also, what I was telling. So you can take A2, A1 and A0, and here you can take the 4 outputs D0 to D7, and here 3 input AND gates are there. So what I told you, that each of the input is going to be replaced by the, so actually each of the gate is going to be replaced, 3 input is going to be replaced by the 2 input AND gate. Okay, you can do it for your just practice purpose. This is not for the submission. Okay, okay, so I request you to give the attendance. I have given the attendance link, so you give the attendance. And submit the assignments by today in the Google Classroom. I have posted already the assignments, 3 assignments I have posted. The simulation part you have to do, and you have to complete it. Okay, so thank you. Next day I will be doing the encoder part and other parts also. So it's a shortage of time, so I should have okay, so I will be posting this one in your classroom. The PPT I am posting in your classroom for sake of your reference. Okay, so thank you. If you have any query, you can just text me.